Well, after a lot of troubleshooting, I finally have this circuit working pretty well. It's still not done. There's a couple more features I'm adding, some little surprises in there that are gonna be pretty cool. But the core functionality I think is done here, and thought I would show it off. So as usual, if we dial a 1, we get a 1. This represents what number we actually dialed. We have it on the 7-segment LED as well as the in binary over here. And then on this screen, we have the number we dialed as well, which is 1. And then down here, we have a 1 represented in binary. If we dial a 2, we get a 2. And then after a short delay, we get a 2 here. And then 3, we get a 3. And we should have 3 here. Now, binary is base 2, unlike our normal decimal system, which is base 10. So in binary, the max number you can have per digit would be 2. So 2 to the 0, to the 1, to the 2, which means that each place represents a specific number if you're converting to decimal. So like the first instance represents a 0 or 1, and then 2. So if we wanted 3, we'd have 2 plus 1 equals 3, right? And so that's basically how binary works. And if we have 8-bit binary, we could go up to 128 plus all of these recursively. So that's what we have going on down here is a binary representation, and that's neat. But what happens if we flip this switch to turn on the second pin? Okay, so now if we dial a 1, that's weird. We're getting a 2 here, and we're getting a 2 down here. Okay, well, let's dial a 3. Okay, so we got a 3 here and a 6 here, and this would be the 4's place, and this is the 2's place, so we'd have 4 plus 2 equals 6. It's a little weird, right? Well, if we go 4, now we're getting an 8 and an 8. So that seems like it's doubling it. Okay, what happens if we turn on 3? So now we have the 2 up and the 1 up, which gives us a 3. Let's dial 1. Now we have 1 and 3. Okay. And 2 and 1 is 3. Okay, so if we dial a 2, now we have 2 and 6 and 6. And 3, 3 and 9, and 8 plus 1 is 9. That kind of seems like multiplication. Yes. So we have some electronic multiplication going on here. Just taking the number that we dial here and multiplying by the number we have there and giving us a result. Now, unfortunately, one thing is the 2 chips that I'm using here don't output binary coded decimal, they output binary. And the 2 chips that are driving these 2 guys expect binary coded decimal. Binary coded decimal only goes up to 0 through 9, and then it repeats for the next digit. So if we take the number 10, for example, in BCD, binary coded decimal, we'd actually have to have 5 bits, 1 bit, and then we would have 0001, right? So we would have 1, which so the first digit would be 1, and the next digit would be 1 or 0, right? So actually it would be 10000, right? But in binary, 10 would simply be 8 plus 2, so it'd be 1010. So anyway, this kind of flips out if you go above the number 9, unfortunately. But that's okay, because these down here show us the real numbers. So we're at 3 times 3. If we did 3 times 4, we'd expect 12, which this isn't going to work. But now we have 8 plus 4, which is 12. So this is the true representation, and this works as long as you're below the number 9. But let's go something a little bit more interesting. If we take and set this for 9. All right, so now we have the 8 and the 1 up, which equals 9. And we can do 1 times 9 is 9. And we'll bring up our conversion chart here. In binary, 1001 is 9, and that's 1 times 9. So if we were to dial a 2, we should expect, again, this isn't going to show properly, but this will show 18. And 18 is 10010, 10010. All right, we can go all the way up to 9 times 9. There we go. 9 times 9 is 81, which is 1 in the 64th, 1 in the 32, and 1 in the 1. So 64 plus 32 plus 1. Oh, I'm sorry, that'd actually be 24. 64 plus 24 plus 1 equals 81. And sure enough, we have 0, 1, 0, 1, 0, 0, 0, 1. Cool. Let's do 5 times 9. 45. 1, 0, 1, 1, 0, 1. 1, 0, 1, 1, 0, 1. Awesome.